So good morning all. In this section we will see some facts related to rectangular waveguide. So rectangular waveguide, as the name suggests it's rectangular in shape, and here you can see a rectangular waveguide, and this is the z-axis, this is the x-axis, and this is the y-axis. Now when we deal with rectangular waveguide, we will be coming across two terms, that is TM mode and TE mode. These are the modes supported by a rectangular waveguide. So what is TM mode? TM mode means transverse magnetic mode. That means the magnetic field should not have any component in the direction of propagation of wave. So here the electromagnetic wave is supposed to move along the z-axis. So in that case, the rectangular waveguide is supposed to support TM mode provided if HZ component is equal to 0. That is written here, magnetic field should not have any component in the direction of propagation of wave. That is, if EM wave propagates in Z direction, there should be no magnetic field component along the Z axis. So here I have drawn the component of electric field and magnetic field for a TM mode, and this is the direction of propagation of our electromagnetic wave, and this arrow mark represents the electric field, and the red line represents the component of electric field vector. This one represents the horizontal component, and this one the vertical component, and obviously the magnetic field will be pointing out of the board. You can find the direction using right hand thumb rule. So here H is out of the board and perpendicular to the direction of propagation, and magnetic field will not have any component along the direction of propagation. That is, Hz is equal to 0. That means in TM mode of a rectangular waveguide, the magnetic field will not be having any component along the z-axis. Its component will be along the x-axis and y-axis. But when we see the electric field, that is E, the electric field will be having component along x, y and z axis. Okay. And where the Ez, the electric field component along the z axis, is given by E naught sine m pi x by a sine n pi y by b exponential minus gamma z, where a and b are the length and breadth of the waveguide. Now ideally this TM mode is represented as Tm small m n, where the m and n are any discrete value which defines the different types of transverse electric mode supported by a rectangular waveguide. Now here I am giving different combination for small m and n. In the first combination both the values are 0. If I substitute small m and small n as 0 in this Ez, you can see the Ez value is equal to 0. That means there is no electric field component along the Z axis. That means this is against the rule of TM mode, because according to TM mode definition, there should be a component for the electric field along the Z axis. So we can say the rectangular mode will not support TM 0, 0. Similarly, if m is equal to 0 and n equal to 1, you will get the Ez value equal to 0, which is also not supported by the rectangular mode. Similarly, when m is equal to 1 and n is equal to 0, also the Ez value is equal to 0, which is not supported by the rectangular mode, and n equal to 1, m equal to 1. In this case, this Ez will be having a value. Hence, this mode is supported by the rectangular mode, and this is a minimum mode that exists in a rectangular waveguide, and this minimum mode is the lowest frequency over which the wave can travel. So the wave which is traveling in this particular mode will be having the lowest frequency that a rectangular waveguide can support. So if you have a wave whose frequency is less than the frequency of this TM11 mode, then that means that wave will not propagate through the rectangular waveguide, because the minimum frequency should be that of TM11 mode. Next we will see TE mode. TE is known as transverse electric mode, and here the electric field will not be having any component along the direction of propagation of wave. That means Ez will be equal to 0. So here I have drawn the components of electromagnetic wave, electric field and magnetic field. This is the direction of propagation, and the arrow represents the direction of magnetic field, and the red line represents the components of the magnetic field, and accordingly the electric field will be pointing into the board, that you can find out using right hand thumb rule. So since electric field is pointing into the board, it will not be having any component along the Z axis. Here magnetic field has component along the Z axis, but no component for E along the Z axis. That is, Ez is equal to 0. It is a just reverse of TM mode. In TM mode, Hz is equal to 0, and in TE mode, Ez is equal to 0. And the Hz component is given by H0 cos m pi by a x cos n pi by b y exponential minus gamma z. And as in the previous case, here also the TE mode, the different TE mode is represented by TE small mn, where m and n can be any discrete values. So here first what I am going to do is I am going to substitute m is equal to 0 and n is equal to 0. So if I substitute m equal to 0 and n equal to 0, what I will get is Hz is equal to H0 exponential minus gamma z, because these two cos term becomes 1. That means Hz is equal to what? H0 e exponential minus gamma z, which is a constant. Now you know an electric field exists only if there is a time varying magnetic field, right? So if this Hz value is equal to 0, then that means, if this Hz value is equal to a constant, that means the field is not time varying, and hence there is no electric field. Therefore Ez is equal to 0 for the condition m equal to 0, n equal to 0. So here it is written, if m is equal to 0, n equal to 0, Hz equal to constant. Since magnetic field is constant, in this case no electric field exists, because only time varying magnetic field produces electric field. So we can say TE00 mode does not exist. Now I am giving the combination M0 and 1. In that case, you will get Hz is equal to H0 cos pi by b y exponential minus gamma z. This is a time varying factor. Okay, that means Hz is time varying, or you can say it is harmonic in nature. Hence, there will be an electric field, and hence TE01 mode exists. Similarly, m equal to 1, n equal to 0, you will get Hz is equal to H0 cos pi by a x exponential gamma z, which is an harmonic factor which produces electric field. Hence TE10 mode also exists. Similarly, if m equal to 1, n equal to 1, again Hz is an harmonic quantity which produces electric field. Hence TE11 mode exists. Now these are the components of TE and TM waves in rectangular waveguide. You are having around 10 components expressions, that is for TE, ESX, ESY, HSX, HSY, HSZ, and for TM, ESZ, ESX, ESY, HSX, and HSY. So the derivation of this above equation you have to do a self-study. The hint is you have to start with equation 26, 27, 28, 29 under the section derivation of rectangular waveguide. So there is a section where you are deriving all the components of a rectangular waveguide excluding Ez in one of the section that we discussed earlier. The video is also available. So you, for this particular section, that is for finding out the expression for components of TE and TM wave in a rectangular waveguide, you have to start from that equation 26, 27, 28 and 29, so that you can do as self-study. Equation 26, 27, 28, 29, already the video is available with notes. Next we will see some parameters connected with this waveguide, not rectangular waveguide, generally a waveguide. First is the cutoff frequency. cutoff frequency is defined as a minimum frequency needed to propagate through a waveguide, which is given by the expression fc is equal to 1 by 2 pi square root of mu epsilon into square root of m pi by the whole square plus n pi by b the whole square. The second factor is phase velocity Vp, which is given by omega by beta is equal to c by square root of 1 minus fc by f the whole square, where c is 1 by square root of mu epsilon. And you can define phase velocity as a speed at which a point of constant phase travels. That means a wave is a continuous signal, right? So if you take different points in that continuous signal, some points will be in phase, and the speed at which those points travels is known as phase velocity. Now here we are seeing three different conditions when f is less than fc. When f is less than fc, what happens to Vp is it becomes imaginary. When f is equal to fc, Vp becomes 0, and when f is greater than fc, Vp becomes real. So if the electromagnetic wave has to propagate through a waveguide, the value of Vp should be real. That means the f represents the frequency of the electromagnetic wave. So this f should be greater than the cutoff frequency. Next term is dominant mode. And the dominant mode is a mode with a minimum cutoff frequency. The mode which has a minimum cutoff frequency is known as dominant mode. And the derivation of cutoff frequency you can do as self-study. Thank you all. That's all in this section.